make presentation for another guest of ICTP-SAIFR, Professor Manuel Asorey. Professor Manuel is from Zaragoza in Spain. He is very well-known expert in several areas like gauge theories, topological materials, quantum gravity, and quantum mechanics. He had brilliant students who made very good career. And for many years, he served as elected head of theoretical physics of Spain. Okay, and today he will tell us about the new gravitational landscape. Manuel.
Thank you. So we are participating in a mini course of quantum gravity, but this colloquium is a different subject. So it's just a reflection on how fast we are moving in understanding gravity these days. Classical gravity. Can you hear me? Ah, okay. So it's a collection of remarks about the latest developments of the field, and as a matter of fact, our landscape from the gravitational viewpoint has changed a lot along the last 2 decades. So let me just remind you what are the most important new developments, and we have to be used. I'm still reluctant to get used to this new perspective, but we have to understand that we have to change our minds to think along the new perspectives. So, first of all, I like to start saying that gravity is the oldest fundamental interaction that mankind knows. It's even written in the Bible that we have to, the sweat of our brow, thanks to that we eat. So during centuries, people have to work hard against gravitational field to make agriculture, to work, to get the food, and also to make transportation. So even if you invent the wheel, you need forces to move. And this is qualitative, but is the first human interaction is gravity. Very recently, we discovered other interactions. For instance, electromagnetism is just 2 centuries old. And it's very, very, very recent. But from scientific viewpoint, we should also thank to gravity the birth of the modern science. Galileo, what he did, apart from other contributions, was to understand mechanics by studying terrestrial gravity. So it was a scientific approach, so it's a quantitative approach, but the basic force was gravity, to understand the behavior of the bodies under Earth gravitation. Short after appeared Mr. Sir Isaac Newton. Maybe this is not working. Oops, So see, this is my favorite landscape, which of course is plenty of gravity effects. You see how the snow is fixed. Is not activated, sorry. So there are a lot of gravitational interactions which set up this very nice landscape in the Spanish Pyrenees. So, but coming to the next step, okay, is just Newton's contribution in the 17th century. He made a huge jump. He showed that the gravitational interaction is the same in Earth than in the solar system. It's few orders of magnitude where this Newton theory was great jump and is essentially the basic starting of modern science, the universal law of gravitation. In fact, he also put the name, gravitation. The bodies gravitate. The second jump is more recently, is Einstein, is general relativity, to make compatible Newton's ideas with the recently discovered special relativity. He was forced to introduce gravity as a field theory, as interaction which propagates at a finite speed, so the speed of light. This could not fit in Newton language, right? For that, he has to invent some mathematics, which is jumping from one field, just the potential, which will accommodate Newton's law to a field theory, let's say, to 10 fields. It's also a mathematical jump. But what is more important from this, let's say, phenomenological perspective, is the fact that he jumped from the solar system to the whole universe. The scope of Einstein's theory, we know today, not at that time, that is many orders of magnitude more important than the Newton's jump. And for the first, has always some predominance, but anyhow, quantitatively speaking, Einstein's jump was much more powerful. Apart from that, the theory he invented was beautiful, mathematically speaking. You understand that this interaction is linked to the geometry of space-time, which is a highly non-trivial idea, and which makes gravity very different from all other interactions. It's attached to the intimate structure of the space-time. And this is the problem for quantizing. We have seen in the parallel sections of this mini course that this is a real problem, to attach gravity to the geometry of space-time. But nevertheless, is what it is. So the Einstein theory, you know, that it was motivated, he wanted to explain, who was motivated from a theoretical viewpoint for understanding what should replace Newton's universal gravitation. But in practice, he was also trying to explain some anomaly which existed in the precision of the Mercury perihelion. You know, when you deal with planets, it's a very nice idea. When you have an anomaly in the solar system, there are two ways of understanding the anomaly. One way is to think that there is another planet or another gravitational object. For instance, these days, some people claim that there is a black hole in the edge of the solar system, which is modifying some behavior at that long distance. The second way of incorporating anomalies is the Einstein way. You just completely modify the theory. Just a minor, a tiny effect implies that you have to throw away everything. So the anomalies, or these days, is very popular to call it tensions. Tensions is a weak way of calling anomalies. Anomalies is more serious. So anomalies, you have to change something. In tensions, they may disappear. But so the first challenge of Einstein was to explain this precision, and he was very successful, although he made a lot of mistakes, but at the very end, he found the right answer to that. The second observational confirmation was the prediction of the deflection of light by matter, according to Einstein's general relativity, was more accurate than the Newton prediction. Newton theory also has explanation for this phenomenon. Essentially, this is connected with the equivalence principle. When you write, for instance, Newton equations, on the left-hand side, you have the acceleration times the mass, and you call it this, the origin of that in the Lagrangian is, you call it inertia, right? The right-hand side, you have the force, the gravitational force, which is the product of the two mass over r squared. If you have one mass in both sides, you can eliminate the mass. And so the equation holds for massless particles. And this is the prediction of Newton's theory about this deviation of light because of the effect of the gravitation of the sun. But Einstein's theory has the same fundamental principle, but the result, numerical result, is different. And this was tested by this Greenwich team going to Sobral here in Brazil and Príncipe in Central Africa. Both points were Portuguese speakers. It's a curiosity, but I mean the eclipse which they were trying to use to measure this was passing this orbit, where the closest points to England were these 2 points. And these are the two leaders of the experiment. You know well this because it was celebrated probably here in Brazil. So I should not explain more, but nevertheless, since I'm here, I would like to put this picture. I mean, I don't have to explain that there are few anomalies also in the experimental setup, which finally conclude that the Einstein prediction was more accurate than Newton's prediction. And this confirmed the validity of Einstein's theory, although let's say the more accurate confirmation was done 1 year later in Australia with another eclipse. But anyhow, this became very popular and Einstein became famous, and I like very much the letter Einstein wrote acknowledging the contribution of English physicists to establishing his theory, in spite of the fact that they were fighting in the war few years before that. So this is a remarkable historical event, but from the gravitational landscape viewpoint, is just one point which tells us that we have to shift from Newton's theory to Einstein's theory. But Einstein's theory predicts many more effects than these two ones, which are the original one. Particularly, it predicts that there are very strange solutions which are known as black holes. And these kind of solutions were found the same year, or perhaps 1 month later than Einstein published his equation by Mr. Schwarzschild. Well, I will not explain. There are many historical remarks how Einstein received his letter from Schwarzschild and the replies, and okay. But he died, Mr. Schwarzschild died a few months later. So the second strange solution of Einstein equations is the Friedman solution, which was found 7 years later by Alexander Friedman, and a bit later, 5 more years, required that Georges Lemaitre rediscovered this solution. The remarkable fact that this solution was not associated to local distribution of matter, like the black hole solution of Schwarzschild. It was thought for a uniform distribution of matter, and which contributed to find a cosmological solution of Einstein equations, which was not the one Einstein liked it. Einstein, you know, he was searching for static solutions, and this one is not static, it's expanding. It took many centuries to understand that this was the, sorry, not centuries, decades, to consolidate this solution as part of our landscape of gravitation. So we are living in one of these solutions of Einstein equations. But many other things were predicted by this Einstein equation, GR. For instance, the system of gravitational waves. Einstein himself found this kind of solutions, but he didn't like any of these solutions. He didn't like the cosmological one, or reasons you know. Also, so what Einstein has in his mind, he was hating singularities. And all these solutions have singularities. In this one, you have the Big Bang. In the Schwarzschild, you have the singularity in the bare points of the solution. And this one do not have singularities, but are necessary to have singularities. Why? Because any kind of way, they produce interference that you can combine, and finally, is telling you that the solution of the motion equations are not unique. You have to fix initial conditions everywhere. And in particular, these waves means that you have too much freedom. Einstein wanted to get rid of the electromagnetic singularities by coupling electromagnetism to gravity, expecting that this merging of the two theories will solve the problem of electromagnetic singularities, and then to have a new theory which have more singularities and even more dramatic than the electromagnetic one was not a good news for Einstein. But nevertheless, he found that, and so years later, he was claiming the opposite, that there were no solutions. Okay, there are nice comments by Pauli about this, but let me just skip. And then it took a few decades, as I said, to confirm that some of these solutions are in our landscape. The first critical transition concerning black holes was done by Roger Penrose, and a bit later by Hawking, dealing with the cosmological solutions by Friedman et al., was the following. So you can have a solution in any theory. There is a famous sentence in Spanish literature from the 30s that there was a famous torero, you know what torero is, bullfighter, which was, very popular, and it was usually invited to the social events with scientists, writers, artists, and all this kind of, let's say, cultivated atmosphere. In practice, there was a famous philosopher, very famous at that time, which was Ortega y Gasset. He was influential in the visit of Einstein to Spain, and he knew Einstein personally. But this torero was introduced to Mr. Ortega, and he asked himself, what are you doing? I'm a philosopher. Well, there are people for everything. This was the answer of the torero. So you can have a theory and can have very strange solutions that maybe never appear in life, okay? And this was the common thought about the black holes. That is, they are solutions, but they do not necessarily occur. So the change of mentality came from two factors. One was Roger Penrose, who discovered that a large family of gravitational configurations evolve in a rigorous way to this Schwarzschild solution. So, to some extent, these solutions are attractors of a lot of configuration. So they are not so strange. They are not, for instance, one could criticize the fact that they are symmetric under rotations and so on. This is very special. So in the universe, you never have such exact symmetry. But this theorem tells you that even if you start with something which is not symmetric, you end up with this, thanks to these no-hair theorems, into that solution. So black holes of the Schwarzschild type and the Kerr type and the later models of black holes are quite natural. They are not, like this torero remarked, strange people which exist always, maybe one, in a million, but it's common, so it's popular. And the second reason for searching for black holes was a paper by Oppenheimer and Snyder in the 30s, who proved that there was a natural start evolution, was grow because it was an equilibrium between, let's say, radiation and gravitational forces, that at some point was, since the evolution was always in this expansive way, at some point they collapse and produce gravitational creation of maybe a black hole, a neutron star, dwarf star, and so on. So in practice, there are mechanisms that universe can create these black holes. So the mathematical perspective, Penrose, and this, let's say, more physical production of black holes, or at least condensed matter stars, lead to the search. Here is the picture by the star evolution. You have two branches depending on the mass of the starting star. If it is small, evolves to create a white dwarf, and if it is larger, well, you end up either with a neutron star or a black hole. So this was a quite popular subject in astronomy, astrophysics, for the 60s and after the Second World War. So, but now the question is, well, there are mechanisms who can create these black holes, so they are not so exotic. They might exist because there are physical mechanisms can create. Question is how we detect them. Well, I mean, you know, physicists think a lot and they find ways. First one is by gravitational lensing effects. Well, even if you don't see the black holes, the light, like in this Eddington experiment, the light can be deviated by the effect of the strong gravitational field created by the black hole. So if you observe deviation of light, like a lens, you can conjecture that you have detected a black hole. But the easiest way to do it is to consider a binary system formed by a black hole and some visible star. And since the star is attracted by the black hole, you will see the effect directly of the black hole in this star. And in fact, this, since the attraction is very strong, this appears in signals in the X-ray domain, which was already well known for that. The other two ways, which appear a bit later, are that if you have a black hole which is inside a domain where you have much more matter, the black hole is swallowing this matter, is trapping, absorbing this matter, and because of the strong action of the black hole, this matter will emit light, and we will see the effects of this attraction by, again, X radiation, X-rays radiation. And the last one is what we have detected recently, which is that even if you have two black holes which are forming a binary, well, if they are so close, they can end up merging. And if you are able to detect the radiation emitted by this merging, of course, in the gravitational wave sense, you can claim that you have detected also two black holes, not one, just two. Okay, these are the ways which were on the list long ago, but in practice, it took a lot of time to use these effects to really detect the first black hole you discovered in the landscape. So till the 60s, there were no black holes. There were conjectures, theoreticians claiming, and so on, but no. And then the first one is in the year 64, is this Cygnus X1, which was a binary with a light star. And so the emission of X-rays confirmed that this was attracted by a black hole with 15 solar masses. So this is the birth of the new black hole physics in astrophysics. The second one, I mean, historically, there are many others. I mean, there are many claims and many publications. But let me just focus on this one, which started to be measured in 92. And it's the black hole which is in the center of our galaxy. Is what is called this Sagittarius A star, okay? So what people observed is that, you see 92 here, that there was a star who was being attracted by some black spot on the center of our galaxy and was moving. They were looking at this star, and you see they were following this motion for many decades, 92 till 2013, here, just to confirm that this orbit was compatible with a massive, supermassive object in this spot of the center of our galaxy. And they deserve a Nobel Prize for this discovery, which took more than 1 decade almost to be discovered. So our landscape now is completed with these strange objects. We have black holes in the world, in the universe. Here is the list of these pathological, let's say, new objects of our landscape, which were listed here before the merging of two black holes in 1915. So you see, you have a kind of neutron stars, which were discovered because they are forming binaries with some more visible objects, and they make X-rays in the spectrum. So you have a list here, many of them. You have also one which are formed by binaries, but with 2 neutron stars, or a neutron star, a neutron and 1 star. In particular, this one, which is here, which is 1913 plus 16. This was very important because allowed to these guys, Hulse and Taylor, discover the system of gravitational radiation. Because the orbit of one of the visible object around the other, which was a neutron star, was closing. So the orbit, the perihelion of the orbit was getting closer and closer to the center, to the neutron star, and they were following a law predicted by the theory, assuming that the radiation which was emitted was in the form of gravitational waves. And you see, even if they gave the Nobel Prize around here, the continuation of this prediction, the fitting of this evolution with general relativity, eventually this object will collapse. They will merge, but it will take a lot of time. So I don't think we will live so long to see this merging. But you see, they are happy because they got the Nobel Prize. So, but this is the day they received the new. And so this is what they were measuring was this, which now took their names, but the official name is this combination of figures. So then, in astronomy at that time, there were also pairs, binaries of white dwarf and neutron stars. So the list is very large. So the universe is populated of these objects. And again here, at the very end of this list, you have binaries of neutron stars. Okay. All these were observed, and so neutron stars exist. There is a lot of them, and not only there is a lot of them because we don't detect all of them, but we detect mainly the ones which are in binaries when you have either visible star or you have lensing effects, okay? And now we start the list with black holes. So there are also many black holes. But before this famous 2015, where the LIGO reported the discovery of emerging of black holes, you have a list of transient galactic black holes. And here are the list of their masses in terms of solar masses. You know, 5 solar masses, 10 till 31. Not very large black holes. If you remember, the black hole at the center of the galaxy is much, much heavier. Later on, we will see that. Because this is part of the landscape we have to learn. It doesn't mean you have to learn all these names, but at least you have to be aware that we are not alone in the galaxy. So here, in magenta, you have the Cygnus X1, which is a persistent black hole in our galaxy. This was the first black hole discovered in the 60s of the past century. And then there are other black holes which are outside our galaxy. This is the picture of black holes before 9 years ago. Not too far away. But then you found so many, even at that time, that you can classify according to their masses. These ones reported in the previous slide were very small, 20 solar masses and so on. But here you have another bunch of black holes discovered using these 4 techniques, which, you know, they have billions of solar masses. So not 20 solar masses, billions solar masses. So these are supermassive black holes. Most of them are at the center of galaxies. So it's another way of looking for black holes. Look at galaxies like we did with the Milky Way. You can do with all this family of galaxies. And you find that there are many of them. Even there are claims that most of them do have a black hole at the center. And also the distance where these black holes are very far apart from Earth. So, you know, 320 million of light years, okay? And this, 1 billion light years. In fact, recently it has been discovered a galaxy hosting a black hole at the center, which is very close to the birth of the decoupling period of recombination period of universe evolution. And in fact, in this case, what astronomers found is that the ratio between the mass of the galaxy and the mass of the black hole in the center is much larger than for the other known galaxies with a black hole at the center. So it means, the interpretation is that this old black hole is the oldest one, according to their distance to the Earth, that was eating most of the matter in the galaxy. So they conjecture that probably this will happen in the future for the rest of the black holes. Please, Nathan. How? No. Here is on the left. You mean? Yeah. So this the uncertainty of the numbers there is very large, but is compared with Neptuno. is where you don't see light around, okay? But it's the most imprecise. I mean, the errors here are very large in all. But you know, also you can ask how do you estimate the mass, no? Yes, but not all of them are obtained in this way. But this is the point. And also the distance. How do they measure the distance? So it's redshift, but it's a black hole. There is no light emission. So the uncertainties are very large. Probably, as you guess, this measure of the mass is because of the trajectory, right? But these are the oldest and the largest black holes we know today. It's impressive, you know, billions of solar masses, okay? So these are the super massive large. But there are others which are not that large, intermediate ones, which are still heavy, I mean, millions of solar masses. In particular, our friend, which is sitting in the Milky Way, is Sagittarius, is, well, this is more or less the size of our galaxy, so it's not very far apart. It's inside the galaxy, right? And you know, is millions of solar masses. It's quite, and this is accurately measured because these people who were measuring the orbit of S2, which was the star going around this ellipse, is quite accurate. So the mass is very large. So there is a gap between these supermassive black holes, which are at the center of the galaxy, of the galaxies, and the ones which are obtained by other methods. For instance, Cygnus, which was not in this slide, but it was maybe here. You see, 15 solar mass is nothing. It's a baby, right? And also the distance of Cygnus, which is not here, is not the closest black hole to Earth, but it's almost. I mean, there are only one or two more closer in our galaxy, okay? So this was the first one because it was very close. This list is telling us two things. One, there are more black holes than expected. You remember that I started doubting of the existence of black holes. Now, the change of landscape is that we have no doubts, but we have too many. So we didn't expect to have so many. So perhaps we have to understand better. In particular, one of the problems is to understand these supermassive black holes, how they were created. And apparently, so they increase their mass by evolution, by eating what is around. But this is conjecture, but it can be solved in the short future. So let me move this one I already commented, and then we come to recent times. So it's not even a decade ago. I mean, next year will be a celebration of the anniversary of this discovery, September 2015. It's made by interferometers. I mean, you know that. I mean, I will not explain in detail. You have what they discovered is that there was a binary made of two black holes, and they merged, and they emit. This was a huge catastrophic event in the universe, and they emit a lot of black hole of energy because the merging object, which remained at the very end, has a mass which was much lower. So the rest of the energy was emitted in form of gravitational waves. So in this experiment, what they detected was the arrival of the gravitational wave emitted by this binary, but they could infer what were the masses, what was the distance, and what was the final mass of the object which remained. Of course, this, you know how they work. I mean, they have templates which obtained by theoreticians with numerical relativity work, and they found which is the closest template approaching these LIGO detectors in US, and they infer from these numerical calculations what is the distance, what are the masses, and so on. So it's impressive. And if there was some doubt, I mean, you see, again, after 1919, Again, they made the front page of many journals in the world. Again, all these journals, you read carefully, they are taking not seriously the result. They are always making jokes with scientific discovery, but anyhow, they have, for instance, look at this New York Times here. They are a little bit not so serious with this discovery. Okay, so what is now the perspective? It changed after this, because now we have a new messenger, which is this gravitational waves. So it's not only optical, telescopes and maybe satellites. You have just these mergers emit so strong gravitational waves that it can be detected on Earth. And so we learn a lot. Because of the merging, which is another mechanism of discovering black holes, this was the first event in September 15. And these two objects where black holes merge and got a larger black hole here, 60 masses, solar masses. But there are other, in 1 year after or 2 years, they discovered other, which this remains as the larger one. Nevertheless, there were the growing number of other black holes with lower masses, and which were measured not by gravitational emission, but by standard X-ray emission, which are much lower masses. Of course, there is another gap down here, which is why you don't have smaller black holes. Well, there are few low bounds, low mass bounds. First is that if it's too small, by Hawking radiation, this evaporates. So no more black holes, except it was formed recently. Then you have the chance of see the last cry of this black hole. But then there are other constraints that even the black holes created with this collapse of the stars, there is a Chandrasekhar limit, which tells you that you cannot go much below. So there are gaps in the spectrum, mass spectrum of black holes. And this is very interesting. So this is a more recent picture. So it's a landscape. This is why I call it landscape. You have quite a lot of black holes obtained by these interferometers, LIGO now with Virgo 2, and a third partner. And you see, you have, but still, now they are higher mass. For instance, this one is the record man, black holes obtained by fusion of binaries, which is 160. So it's quite large, solar masses. But you have a small here. You have also new neutron stars. This is the map of neutron stars, which were also obtained by this LIGO Virgo, measuring gravitational waves. And even more, this is more recent, is the last, I think is the third observational period of this LIGO Virgo Henkagra now in Japan. And then you have more, but still, here is 200. So this picture, this landscape grows in mass and will continue to grow. So, and also from below, you have more mergings in this area where you have very small masses, okay? You have still some neutron, family of neutrons. This way of picturing, you have to be used. Instead of putting all of them together, you split it in this way, you can put more on the same plane, right? And you keep obtaining other black holes. These red ones are also black holes, but they are not merging. They are the ones which are with a binary, which is telling that there is a black hole there. All of that in this scale of masses. So we have to knew that our universe is plenty of black holes. So what are the next steps? The next steps are going beyond in all black holes. Yes, most of the black holes here, the more distant one is this one obtained in 19 year in May. So, which is at Z 0.82, which is quite far away, but not, I mean, too much. So we wanted to learn more on cosmology in the dark periods here. And for that, there is a proposal which is making Einstein telescope, which is essentially improvement of this LIGO going underground, okay? But this is still to be shown. So this is maybe the next step in Europe. But we have today this James Webb satellite, which is continuously discovering things. For instance, so this is today, it's not today, the day today, just, I mean today in these terms of landscape. Here is a supernova discovered in Cassiopeia, and this is this year discovery. You have also the merging of two galaxies here. It's impressive. So the data from James Webb is very impressive because they are cleaner, more precise, and even at the long distance. Okay, but let's come back to I mean, I think in this room, most of you are theoreticians, I guess, no? Although Rogerio perhaps will not be like to be considered only theoretician plus astrophysicist or cosmology. So, so this is one problem that gravitational waves can try to understand better than we understand now. Is the history of evolution of the Hubble constant. Here you have the first measure of the Hubble constant made by Lemaitre, which is more than 600 in units, kilometers per second per megaparsec. Okay, then is the Hubble one here, because this is increasing. So you see that this was, people continue to measure, and then in the 60s, there was a collapse between 100 and 50. And some people joke about that, saying that the people living in the west coast of the US have 100, but the people living in the east coast, which are teams of astronomers, of course, have 50. So the difference is, let's say, 50 in units today. Today, till the year 2000. But now, you know, this does not stop. I mean, and so today we have what is called the Hubble tension, is the measure of the same thing. But now you see there are people who are finding 68, remember, 50 and 100, okay? Now, the situation, which is called anomalous, because this is how they call it, is between 68, let's say, roughly speaking, and 73. Well, I mean, some observations are with large errors, but the tiny one here is this one here, and also this one. So they have a small error bar, okay? This holy cow is also small, but not that small. Different techniques to measure, essentially looking for supernovas, type 1a. And these are more cosmological data coming from large-scale structure and barium variation, and then also by cosmic microwave background. So there is a discrepancy between these values and these values. But remember, the discrepancy a few decades ago was between 50 and 100. So now we are claiming 5 units. So being positivist, the situation improve a lot. So the controversy means, you see here, people trying to combine both, claim that they have a discrepancy which is 6 sigma, right? This result. By the way, there is another one here which is trying to interpolate between two. I will not discuss that, but what I will say is that the gravitational landscape can clarify this in the future in the following way. All these data are optical, optical data. So these are huge collaborations. This is with satellite. This one are with observatories in Earth. And these ones are also observatories, but looking for supernova. So even it's already published by the team of LIGO that they were measuring one event, which was a merging of a neutron star and a black hole. The result was a kilonova, which during the whole period, you have some emission in the optical spectrum. So you could measure by redshift, measuring the redshift of this optical light, you could measure one of the elements which enter in the Hubble constant, which is the distance and the speed. Okay, what you measure with the redshift is the speed, how fast this is going away from our point. And then the rest, the distance, is measured by these numerical templates. Of course, the error is quite large, and this is why does not clarify the situation. So another picture of the same here, on the same scale. Here you have the early universe measurements of this H naught, and here you have late, because supernovas are very close in time with the present. So the solution by gravitational waves is in the middle, but error bar is enormous. But this will increase a lot the number of events of this type in the future. So when you have a larger statistics, you probably will be able to solve this puzzle with thanks to the gravitational wave. But anyhow, this shows you that the gravitation interaction, of course, everything is gravitational here, because after all, Hubble has to do with the solution of Freeman and so on. But I mean, the latest gravitational idea is to have gravitational waves. So now, from solutions of Einstein equations, we have lensing, black holes, gravitational waves, and cosmological solutions. All of them combined here. So let me just conclude with two more remarks, which make for theoreticians more comfortable. I don't know why, but most of the observational data can be fitted by a modification of Einstein equation. First of all, the current cosmological model is lambda CDM, which means that the dark energy in that model is controlled by a constant in the cosmological constant in the Einstein Lagrangian. So you can arrange the model just by plugging one extra term in the Lagrangian. But also, if you want to describe inflation, the best model of inflation, which accommodates to the Planck data, the ratio tensor scalar in this microwave radiation, is given with a small number alpha in the Starobinsky inflation, which is again R squared. And this, for theoreticians, as we are, is very good news, because still with local actions, we can describe a lot of effects at cosmological scales. And so having so simple explanation is nice. So here is the fitting of the Starobinsky model with this tensor to scalar ratio fitted in terms of the primordial tilt. And you see, this is the R2 model, and all other models fail far from being okay. Let me now come to the other extreme. Short distance. Is Einstein theory, or even Newton theory, right at short distance? So we should not forget, because there is also an improvement in measurement of gravity at short distance. 1 decade ago, the record was below the centimeter, but not very much. Now we're in the micron. So people have reduced the uncertainty in the measure of, well, what is plotted here is assuming that there is an extra force, which is not Newtonian, 1 over r squared. It's a Yukawa 1. You have alpha exponential minus lambda r divided by r. Okay, this is a Yukawa-like potential. These are the two parameters which enter into the Yukawa. And as you see in this plot, the excluding domain is approaching to 0 or to small scales. You see here, lambda in meters is this size. So here is the dark energy scale, but you see, I mean, this green region is quite recently, is 4 years ago, okay? The measurement of this. But you have even more. People have refined the measurement of Newton constant. Newton constant is the world measure constant in the fundamental theories. The errors are much larger than the alpha in electromagnetism and the other, and h bar. H bar, alpha, and Newton's constant are the three fundamental constants. And this one you see here, you have large errors, so just 3 numbers after the dot. So here is the value, and here you see the lot of experiments, and the latest one are these experiments here. You see the error now is very reduced, but nevertheless, still not as good as the ones in electromagnetism. And to finally, the last slide, almost, is this excluding domain. So now we have a landscape where we have a lot of black holes, but we see that there are barriers. There is one barrier at large masses. So this is the plot of masses with radius. Nathan asked about how to measure radius. So this line here measures, is the Schwarzschild formula, which connects the mass with the radius. Okay. So beyond that is forbidden. You cannot have more than that. And the other excluding domain is the quantum limit. Let me just tell you one question. Why the electron is not a black hole? If the electron is a classical particle, it's point-like because it's fundamental, has no structure. It should be a black hole, according to classical Einstein theory. But it is not because it's a quantum particle. Being a quantum particle has a quantum length, which is forbids for him. You cannot have a static point-like electron at one point. It's the Heisenberg uncertainty principle. So this is the meaning of this lower one here. And the rest of the universe is here. So this is our gravitational landscape in this two-dimensional plot. Okay? And here you have the different contributions to the different effects. I don't have time to explain because time is over. So we have two limits in our landscape of gravitation. One is not too large masses. The other one is not too short distance. And so gravity is limited by these two. But nevertheless, we have a very large landscape, and we have a good news is that this landscape is plenty of black holes. Even there are people who claim that most of the dark matter missing in this cosmological model can come from these black holes. And at least significant part of this dark component of the matter can be populated by black holes. What is primordial black holes were created at the beginning of the story of the universe. So, second thing is that Einstein is still alive and covers most of our landscape. There are a limited short distance and a large distance, or large masses, sorry. And the good news is that we have new tools to go beyond. The gravitational radiation is very interesting because it's a new baby in our hands. And maybe the ultimate cosmological model now is outside, but still some windows open here and there. So there are still something to understand. But the last word, I will say, is that in the whole picture I made, landscape of gravitation, no room for quantum gravity. It's about new, but maybe in one decade we will have the same blooming of ideas that there will be something to add in the last comment. Thank you very much. Questions? Okay, go.
Do we know why there's such a huge gap between the mass of the Milky Way's black hole and other black holes? Like, ours is like 5 million solar masses, right? And the other galaxies, we find some ones with like billions of solar masses. It's a very big difference, right? So
Yes, but there is no theoretical explanation so far. People working on primordial black holes, they explain some gaps which you find in the spectrum of masses of black holes, but they cannot explain everything. So the main claim, what changed in this kind of approach was that in the past, the similar approach for that matter was called MECHO, which was, compact black bodies. We could explain they were not black holes, but black holes are MECHOs in this sense. They failed to explain, and they were discarded because they were putting all these objects of the same size, essentially, more or less the same scale. The new ideas here is that you have to have, because observational you find it, this large difference. So if you have a distribution of masses which is not uniform, you can escape many of the exclusion limits they have in the past. But it's not well settled. So the explanation of this gap is an open window for theory in the future.
I see. Thank you, Professor.
You said there is presently no quantum gravity in this landscape that you showed, but there is already some people trying to do quantum gravitational corrections to the gravitational wave signals, like scattering of black holes and trying to see if there is some, and because of the precision of those experiments, there might be some window there. What can you say about that kind of?
So far, nothing. What I would say is that these experiments are quantum from the optics viewpoint. So they are perfect, but the errors they have in measuring gravitational waves are much larger than the ones you expect if you take into account the quantum effects. So one experiment which will be crucial will be the following. The photoelectric. So instead of photoelectric, the gravitoelectric experiment. So this is how the photon was discovered. Photoelectric effect. You throw light, classical light, to a metal, and you expel electrons from the orbits in atoms, okay? So if you do the same with gravitational waves, it means that at some point, this gravitational wave is made of gravitons, infinite number of gravitons. But if one of them hits, because their frequency is very high, hits this atom and excites some electron in this atom, it could be measured. The only problem for that is that the order of magnitude is 10 to minus 43 orders of magnitude with respect to the photoelectric effect. So expectations is not very high. But this will prove that there is a quantum gravity effect in the plane waves.
there are experiments being developed in that direction? or-
Yes, even
Yeah.
tabletop experiments and so on, yes.
Tabletop detecting gravitational waves.
Yes. But I will not report on that. I mean,
I have a question. Do we know the proportion of the energy or mass of the universe in black holes, and is it increasing or
no,
decreasing?
this is
or-
debate. It's a debate. Depends to who you ask. I have some friends that say 100% black holes. And probably you know these people too. No, I mean, I prefer not to enter because, first of all, I don't know. And second, the number of opinions are quite diverse. There are people who say negligible. Black holes are negligible for that matter. But other papers say 100%. So it's but it's interesting. So I think I wanted to transmit, for me was the impression when I prepared this talk for other lecture, that unexpectedly the number of black holes is not zero. So it's larger than we expected. I was born before black holes were exist, so I'm the old generation. So for me it was very impressive to see that they are living objects.
More questions? If not, let's thank the speaker.